Hope you guys are doing good. I'm busy preparing for your Christmas plans. Nice to have you all here. My name is Ananth. I'm one of the co-founders of Darwinium. Darwinium is a security and fraud prevention platform wherein we are trying to provide continuous customer protection across every digital touchpoint facilitated by its unique deployment pattern. We deploy our engine on edge, and that's how we protect every digital footprint that an end user of our customers are interacting with their digital assets. I'll explain what it means in diagrams soon. But we're also, I'd like to add, we're also the co-founding team of ThreatMetrics, which got sold to LexisNexis in 2018, and one of the well-known Aussie startups. That's a bit of introduction about Darwinium and a little bit about what we mean by continuous protection. So most of the securities and fraud prevention solutions today are siloed in nature, wherein they basically, what is this? Sorry. I'll put it like this. Where there is a gap in the current industry wherein the amount of touch points you get from the end user is very limited for current security solutions. So what we went about and built is a system which can continuously profile an end user's journey. We call it journey because the end user is trying to interact with the digital asset in a continuous way. For example, in this picture, what we are seeing is a user has browsed the website and optionally created an account and tried to log in and make a reservation and then do payment. And how do we go about protecting that digital website? For example, let's say an Amazon marketplace kind of website. How do we go about continuously profiling that end user and then protecting the Amazon asset there in this scenario from fraud and cybersecurity use cases? And we do this being operating at the edge, and we do it in a very privacy-aware way.
Give full screen.
It's rolling. Sorry, this is okay. I think I can't full screen because of the issues. It's rolling fast. So Clickhouse has been an integral part of our journey, and today's talk I'm going to talk about how Clickhouse has helped us scale to the volumes we have, and how it has helped in various aspects of our core philosophy. Our core philosophy has been, we should be quick in terms of time to value, we should be agile, and we should be cost efficient. And whatever we are seeing in the red fonts there is where Clickhouse definitely made an impact. Basically, it helped us gain insights from day one. It helped us leverage our existing infrastructure in a great way. We had great success in doing minimal engineering. Someone else was talking about in the previous talk as well. How do we go about doing minimal engineering? And it's been a great success story in terms of reducing costs. I don't know if you guys are aware, but data grows quickly, and also comes the headache of costs. Like you spend a lot more amount than you really want, and Clickhouse has helped us in controlling that cost to a great extent because of the engine architecture they have. And it also helped us in a lot of analytics use cases, which is also more about cross-organization relevance. Here is our hierarchy of risk evolution visualization. At the core is the complete visibility that we wanted. Basically, we wanted a capability to analyze every end user's footprint. Like this could be millions of individual interaction points for a given in a given day. And on top of this base data, we enrich it and we take decisions on top of it. And these decisions are taken at the edge at 100 millisecond turnaround times. Our engine is what we call a true real-time engine, and Clickhouse is forming the analytical component of that ecosystem. And finally, we let our customers take actions on this. I'll give an example. Let's say an end user has logged in using an email, and the login has been executed in the US, and in 10 minutes later we see an email logging in from Sydney, we could profile that and say that this is not physically possible. We can reject the transaction or login or account creation, whatever be the end user workflow. We tend to block it by means of letting our customers write rules and deploy machine learning models on the edge. That's where the engine sits, and all this data is being continuously collected inside the Clickhouse database for post-event analysis, and also helping write better rules and build machine learning models in a better way as an iterative process. So the Clickhouse forms the analytical side of it, the real-time engine forms the decisioning part of it. Now I'll move on to the main features built by Clickhouse using Clickhouse. So here is a figurative representation of our architecture, a very, very simplistic view. In the colored boxes there, we have the browser and our mobile SDK, which are basically the starting points of a user's interaction with the digital website. And the digital website could be deployed on an edge CDN, and Darwinium has got this unique solution wherein we deploy this real-time engine component as a distributed component, and this component sits on the edge. So be it your Cloudflares or CloudFronts, and Akamai is coming soon. We let this engine operate by intercepting transparently without the website owner even trying to change their website. Unlike other solutions wherein a user has to change their website every time you want to put in these tags or this kind of frictionless point, we do it in a very transparent way by deploying ourselves on the edge. And we intercept the traffic and help the users take decisions based on your rules or machine learning models. And this data is then pumped into our SaaS servers, which then interact with our Clickhouse engine to store the data and analyze the data. Now, coming to how Clickhouse has helped us, basically, if you look at this primary use case of ours, what we wanted was a database which could capture billions of rows. That has been our primary requirement. Because user interactions are pretty volume in nature, we basically needed a data engine which could host billions of rows, and of course low latency requirements is a no-brainer there, because we wanted our analysts to analyze digital behaviors. For example, is this user typing the same way as they have typed in the last 5 login attempts, as an example. We profile every interaction with respect to keyboards, swipe, touch, and these kind of gestures. We also profile the devices. For example, we could differentiate between a same iPhone model from the one you are using to the one your neighbor is using, kind of use cases. And all these rich interactions means that we wanted an engine which is very powerful in terms of analysis. The other requirement was, since we are a SaaS solution, we needed some sort of partitioning strategy, because one database could host multiple use cases for multiple customers. That's been our core requirement. And the other requirement has been that we needed somehow a capability to distribute the execution logic as well, in the sense that we don't want one server to take all the query load. If there were a better way to distribute the load itself across servers, we could better serve in terms of latencies. And Clickhouse has been a great story for us in meeting all these requirements. And we evaluated other database engines before coming to this conclusion. The next area where Clickhouse helped us is our use case around thousands of columns. Now, many people tend to normalize the data, but our approach has been taking a denormalized approach, like some other batch processing systems like Hadoop-based ecosystems. And we took a similar approach primarily because each interaction the real-time engine did for us had more than a few thousands of columns per row. I mean, if you imagine one interaction the user is having, we had easily 3,000 plus. Maybe even 4,000. We stopped counting because it goes on an every release. But essentially, we have the problem of thousands of columns being part of every row, and Clickhouse was able to support it. Initially, we went the approach of, we will let our customers choose the database engine and we will write to it, more like a pluggable database engine. But we ended up abandoning that idea because, for example, not many databases even supported the use case of thousands of columns. The other use case which really made a difference is rich data types. I know some database engines today have it, But for us, it has been really a big differentiator because when we said, as I said, we have machine learning models executing on the edge or on the API server, which is a SaaS server equivalent of an Analytical system. We had the scenario of end users or the analysts, fraud analysts, trying to define features which are being used as part of the machine learning model. And we wanted a data structure which could host multiple features. In other words, a customer could use 100 features, another customer could use 1,000 features as part of that model ecosystem. And we wanted something that could support an extensible data structure, and maps were a great example of that. We also found tuples to be really useful, which is more like a table within a table kind of data structure, and it helps you in compacting. If you have thousands of columns, maybe you can group some columns as more like a mini table data structure and put it as part of one single column definition. Codecs are another example of where Clickhouse made a difference. I believe the first speaker, Tom, talked about it a little bit, but I can say that that's made a lot of difference in terms of storage aspect as well. And the last 2 points there, what you see are more about differentiating features, I would say. The reason I say this is, as a fraud analyst or a security analyst, you end up having a need to analyze data in a more complex way. It's not about just simple counts. There is a whole catalog of functions from Clickhouse, and maybe it will deserve its own conference if you really want to take to that level. I know Paul is agreeing there, but it's really rich. You'll be surprised when some of our customer-facing data scientists say that I'm really happy with Clickhouse as compared to a previous system they had. It basically decreases your time to analyze to a very great extent. And that makes a difference in terms of your everyday business time, or time you spend on your human personnel trying to come to a resolution on a case. And it has got not only that, but I would say every release, if you look at every Clickhouse release, they bring in nice concepts, small functions which make a difference in terms of your analytical capability. For example, last release they brought NumPy array support. And who thinks of these use cases? I don't know. I mean, kudos to the product team. I'm really a fan of Clickhouse product teams in that case because they really bring true value in terms of analytics, and that's what we love with respect to Clickhouse there. I'll take a few more examples as to how Clickhouse helped us in our journey. There were scenarios wherein we had to do ticker graphs, and when I say ticker graphs, at one hand you're having millions of events coming in. Millions of events getting ingested into your database, but at the same time you had visualization requirements which needed to generate basically ticking visualization of your data. And in a traditional database, if you want to query the data, you end up not being able to do a ticker scenario because you end up taking a few seconds even to complete a query. And with Clickhouse, we actually had a very interesting and clean implementation wherein we used the sketching capabilities. I don't know how many of you are familiar with sketches here, data sketches, the hyperlog and these kind of sketch implementations. If you guys are familiar, they help you have an approximate count, approximate values. Underneath they are probabilistic data structures, but essentially they help you in getting an approximate answer in a very low latency way. And what we used for these use cases was build upon sketches, and it's not just sketches in a single machine doing the sketch resolution. We basically were able to get sketches in a mergeable way. Mergeable sketches are more powerful in the sense that you have multiple shards in your Clickhouse cluster, and you want to merge individual shard values as one single answer, and that answer is the approximate of the individual distributed shard values. And sketches were one such example. We also could do things like heavy hitters. For example, in our use case, our real-time engine generates signals, and if you want to query like what are the most common signals generated in this geography, sliced by this device type, for example, iPhone. And the signals could be that, suspicious device or user typing Unify. Basically, it's a domain-specific signal that is generated by the real-time engine. And what we wanted was surface up the most common signals in the last n minutes. N minutes could be a user-defined window. or a sliding window. It was flexible because we could merge it. We could both implement fixed time windows as a query, pattern itself as simple as an SQL query, and that brings the true power of ClickHouse in terms of real-time dashboarding components. We also could do quantize, which is a very good insight into distribution metrics like 50 percentile, 98th percentile, 99th percentile kind of things. I'll move on to the cloud native aspects of it. I think ClickHouse meetup in AWS offices is a very nice timing for this. We built around ClickHouse and leveraged AWS ecosystem to a very great extent. And that actually formed the crux of our, for example, cost effectiveness and all these kind of advantages. So first thing is ClickHouse provided something called as disks, and I think it is one of the first clean implementations, or one of the few implementations that does separation between compute and storage. There are other databases which do that, but as you reckon, it helps in a very clean architecture if you separate your compute and storage more along the lines of if your writes are heavy, especially in a security and fraud use cases, your writes will be too much as compared to reads, as an example. And these kind of scenarios you could leverage using a decoupled compute and storage in a very effective way. We also had utilized the disks concept to do tied storage. This is very much a core requirement of our business principle, right? Essentially, the fast data is really the most used data. Also, the most recent data is the most used data. As data ages, the utility goes down. And so we had this interesting business paradigm wherein old data was being queried less. So we were able to implement a tied storage in ClickHouse, wherein the most recent data was on a local SSD. That's how we provisioned our ClickHouse node in AWS. We got a storage optimized instance, and then we structured our table definition to just use the local SSD for the hot data. And as time aged, the data got moved onto a S3 disk, which helped in moving the data into a lower cost solution as time evolved by, and that kept all parties happy. The other thing is we used AWS S3 disks for backups. Essentially, when you want to take a backup, if a local disk doesn't hold your backup size, then you run into problems. How do you do backups, especially incremental backups or full backups? Having an infinite disk like an S3 bucket essentially simplified our backup strategies as well. Like you could attach basically a very large unlimited storage kind of thing to an instance and do backups. But having said that, I would say ClickHouse Cloud is the way to go. There's a lot more which ClickHouse Cloud does. Essentially, it's a much better architecture in terms of separated compute and storage. The other aspect is, ClickHouse, people say columnars and databases, but some in the business might argue the disadvantage of a columnar database. But I think we found a very cool application of a columnar database and at the intersection of privacy. What I mean is, of course, ClickHouse is columnar, but what if you're using ClickHouse to generate the pointer to a data blob inside an S3 disk as part of your query? In other words, you could do normal aggregation or analytical queries on ClickHouse the usual way, like others pointed out. But what you could use ClickHouse is also for making queries in such a way that the response of the query is a S3 disk pointer or S3 blob, and that S3 blob is your entire row. So essentially, you're compressing your row as an S3 object, putting it into the bucket here, S3 bucket, which is a separate standalone bucket, and your query reads ClickHouse, the reading client reads from ClickHouse and fetches the entire row from the bucket. The advantage being that from a privacy viewpoint, we made this a customer-controlled bucket. That means Darwinium did not have access to PII data in that bucket. So the edge worker directly wrote the row into the bucket. And SaaS versions did not need to have access to PII data at all. They just queried the data, got the pointer, and then fetched the actual PII value data into the browser directly. That's the gist of the summary. There are a few things involved there, but that's the gist that I think is a very neat architecture for people who are building solutions on columnar databases like Clickhouse. And we also solve the problem of customer privacy to a great extent, right? Because customers would not like to give their PII data into a SaaS service because of this privacy concern. It helped us in conveying that message in a very strong way. The other things that Clickhouse helped us with is basically Codex, as someone said. It has got the concept of TTL. That means you can basically time out your data in a very efficient way without needing for additional pipelines. It also helped us with hot versus cold definitions, and it also has caching constructs if you guys want to play around with it. In our case, we had data in S3, but we also configured a local EBS disk as a cache disk. So when it was being read, there's the other way of caching wherein the S3 blob file was saved on an EBS disk locally as a caching construct. So this is in addition to hot versus cold data. If you, for example, if you're querying a particular entity in a richer way, it could help in latencies as well. Darwinium also went in for AWS Marketplace certification recently, and all I want to convey here is that the replicated merge tree family is a very good, will be a very good friend if you're thinking of getting AWS certified in your ecosystem. The reason being, you write to one shard of the replica and it gets automatically distributed to your, for example, multiple availability zones, and that gives you the cleaner engineering pipeline implementation wherein you're writing to one or even round robin and the servers coordinate to balance automatically. Coming to the data pipeline side of things, where it helped us is data deduplication. I don't know how many of you have implemented a pipeline in production which runs in millions of events, but data deduplication is a very difficult concept to achieve. And our approach has been a little bit different, wherein we accepted the fact that there could be duplicates, but duplicates are resolved on a read pathway, not on the write pathway. So there is a small window of chance that there could be duplicates, but we wrote our Clickhouse queries to deduplicate on read, and that served us in a very neat way as well. Coming to the client ecosystem, Clickhouse has got some good client ecosystems, but for us, Go has been the best fit because it's been richer. I believe it is one of the first clients in terms of its capabilities to have a varied richness, and also Go went well with our temporal workflow engine. So we basically chose Go as a client, and we use a batch append. So we append millions of rows, whatever be the configured batch size, as a batch, and not like one row by one row. We basically take a chunk of events, we do an insert, and that's how we are writing into a Clickhouse server. And the last piece that helps in our case is keep an eye on Clickhouse Keeper. If you guys are part of Zookeeper ecosystems, basically your use cases for global counters or coordination or service watches kind of scenarios, Clickhouse Keeper is a good alternative, and you do not invest in another distributed coordinating mechanisms in your ecosystem if you have Clickhouse Keeper. The other piece that is really useful to know is Clickhouse does support async inserts, which basically helps you in generating lesser parts as your traffic throughput goes high. For example, on the left you have 3 clients writing to Clickhouse done in a normal mini batch way. You produce 3 parts on the server, which would usually lead to compaction issues like any other server. But there is a neat feature for async insert in Clickhouse, which you can use the Clickhouse server to compact on your behalf, so it becomes independent of your client threads. So even if you have 5 or 10 client threads, Clickhouse will do the part generation on the server side, which will help you with the this last piece I think is more futuristic, but this is my biggest bet for the next year for Clickhouse. I think Nidal and folks here might agree that vector databases are becoming a norm and use cases, but there's also this pattern in Clickhouse which you could use to merge a immutable row coming in from a real-time ingest like ours. The events are getting ingested. This could be a table with billions of rows, but what you could have is a dictionary which basically can be enriched in terms of offline enrichment. Imagine this to be a Python pipeline, distributed pipeline, and near real-time enrichment. You can write it into a dictionary table, and a join is actually a lookup of this particular row entity inside this dictionary. In other words, you're not doing a true join, but you're doing a lookup in a dictionary for the relevant columns in that rows which are being processed. So you could tune your queries to actually to have use cases of joins being performed in a very, very latency-aware way. And I say this is more from a vector databases because you could do, for example, embeddings getting generated in an offline way, getting written into this dictionary, and then you could join embedding using UDFs with a normal data flow like this, and that I think will be an interesting use case to consider. I think I'm running out of time, so I'll just be quick here. I think whatever I'm talking right now is an interesting, very recent development, which is you could embed Clickhouse as a server within a process, and that process could be a Python process. So this becomes essentially your embedded server. Imagine if you guys have worked with DuckDB, it's a similar thing to that construct, wherein you could embed an entire server, or even a Lambda for that matter. I don't know whether anyone who is using Lambda, ClickHouse embedded inside a Lambda function, but definitely inside a Python process is feasible now, which essentially means that it gives some very beautiful use cases going forward. People who are coming from Spark, SQL kind of ecosystems may find this as an interesting alternative. And I believe next year you'll see a lot of patterns in this, wherein you're using pure Pythonic native ecosystem to do your data processing, wherein you're embedding a ClickHouse server. Imagine in this framework, I'm using Ray here because it's a powerful unified compute framework for a lot of Python use cases, and it's got some great design underneath it, which is the Ray actor system. And what it's missing currently is an SQL equivalent of a Spark SQL kind of thing. But what I think we could do as a data engineer is basically think of implementations like this, wherein you could embed a ClickHouse server as an actor within your Ray system, and there you get the power of rich functions of ClickHouse as a SQL query. Imagine you're letting your data analysts write a SQL query, and the Pythonic framework is doing a distributed processing of the data by just using SQL as it just like Spark SQL, and with the additional advantage that you're having a first-class Python ecosystem as part of the foundation. So you can do your data preps, your feature engineering. The feature engineering itself could be in SQL-based or a Pythonic way of doing feature engineering, which could then be persisted back into S3s or other ecosystems. So that's where I think the future would be with things like this, and I think it's an exciting time to be in the space, and especially analytics engineering, wherein you can optimize based on the cloud provider you're running on and the complex features you need to build using these ecosystems. That's it from my end. Thanks everyone for your time.